recording. And nobody helped me remember that, by the way. But that said, it's actually a really neat way to use matrices too, so you'll miss out on that a bit. But it does present an okay way to finish up the class. So the last thing we'll do is the homework 11.4, raise the roof homework. And then those days will be just sort of class meetings, like the office hours where you can pop in for help and that sort of thing. So yeah, that's a bummer. But and then even worse, if you can imagine, that also means, of course, the exams scheduled for the last weekend of school, we're just gonna not do. Yep. So that means that grade wise, that will help grades a little bit. So you can focus on finishing up all the homework strong. If you have been thinking of a project that could still go forward, that's okay. But that's what it is. Let's talk a little bit about what we've been doing with the labs. So many of you have finished the lab B, which is taking a look at a couple different types of shapes of mirrors. I've got good examples here that we would have used if we were in class, although since we're out, I didn't have enough to share. So that's why you all had to go get spoons and things. Spoons do work fairly well though. So we had two types of mirrors that I wanted you to play around with. One of them is a convex mirror. A convex mirror is one where the center of it is the near point and then the rest of the mirror folds or bends away from it. And then the other is a concave mirror where the center is the deepest part. So it's like you're looking into a cave a bit. Both of these are examples of spherical mirrors because they are parts of a sphere. And so over the next couple days in our class meetings, we're going to be talking about specifics about what we can learn about these. But let's take a look, grab your lab B from there, and let's chat a little bit about the images that we can observe just through a spoon or by using that flexible mirror and bending it a little. And if you've got those materials handy, grab them as well, whether you've just got the flexible mirror or if you do have a spoon that you can quickly run and grab, because we'll be looking at those images. Okay, so if you've got your flexible mirror here, staring at it into the image, you should see an image that is the same size as you, but as we discussed, flipped left to right. But then if you use your fingers, so I'm going to carefully do it like this and then bend it the center away from me, we see a little transition period, and then after it adjusts, what happened to your image? Or this could be the inside of a spoon, the part that can hold soup. What happened to that image? Still handsome.
Flips upside down.
But it's upside down.
Looks to me like it went upside down and got a little compressed.
Yeah, certainly compressed, and that's partly due to just the shape that we're deforming this in. It's a little, you don't see the compression if you have a really nice smooth mirror like this, but this is also different in in other ways. It's curved spherically rather than just in the Y dimension that we were doing it. And so it looks less compressed in one dimension, but it is smaller. And that's what makes this one look compressed, right? Because it's getting smaller in the vertical direction when I do it like this, but it is not getting smaller in the horizontal direction. So you look squished. But the result is, or if you look through a spoon, you should see a smaller image of yourself. What happens when I push from the back and deflect it like this? Well, I get squished again, but now I don't go upside down. So when I'm deforming it like this, so it's curved, the sides go away from me, I get a smaller but upright image. So when we're looking at the lab B for that, all of these are flipping left to right. But the concave mirror makes a smaller upside down image. The convex mirror makes a smaller right side up image. But then the hard thing to see where you needed the extra light, or if you had, if you went up and got your makeup mirror, like so, these are mine. I can't even put the clips into my hair. This is a really nice example because it is so smooth and everything. The whole purpose of this is to be a mirror that is only part of a very large sphere. And what happens then is that you get an enlarged and upright image, which is quite a bit different from what we saw by bending this mirror away from us that made a smaller upside down image. So we're going to be exploring over the next few days what we can do with that. Now, normally speaking, if we were in the classroom, we would be able to make some nice measurements with these mirrors. In particular, the concave mirror. We can actually use this to reflect an image and create an image projected onto something like paper and do some measurements with that. Plane mirror, even though we bend it, we can't do that. And so we can't fully do that experiment, and so that's why it's not part of it. But I did link some videos, which I'll pop over and show you. Oh, I gotta stop sharing. I gotta go over and get out of the grading section of that so I don't accidentally do that. Okay, that'll work. There's a series of videos that I have found that illustrate this really, really well, and I encourage you to take a look at them. I put them in a separate folder here in class meeting recordings. Oh, no, a special playlist, the spherical mirror demos. It's got a professor who has done this with really giant mirrors and camera angles that allow you to see what you should be able to see through these mirrors. And he goes through and highlights it really well. And then there is the fourth video does a little bit of the measurements that we could have seen with that. And we will see through diagrams, but we won't be able to see fully for the in experiment in this form. Okay, so definitely watch those as part of a homework. But let's talk a little bit about what can we start doing with the ray tracing and everything. So we looked at ray tracing on plane mirrors last week. And we saw that we could use some straight lines coming off of an object that would show us where the image is going to be. And we could even make some measurements based on that image. We're going to do the same thing now with some spherical mirrors. So I'm going to share my screen. This would be an excellent thing to sketch down. Realize that right now when you're sketching quickly, you won't be able to make very accurate measurements, but as we go through, I will hopefully be able to help you figure out how to do this, because part of the next homework assignment, part of the objectives for this unit are to be able to use these ray tracing diagrams to accurately make some measurements. So, where is that one? There. So I have set up here a spherical mirror. And so the couple things are going on here. Through the center of any of our diagrams, we've got the optical axis, which is sometimes referred to as a principal axis. That's what your textbook uses. I have found optical axis maybe is a more common one, but either way, they mean the same thing. And I've got right here a spherical mirror. You can see my cursor, right? Okay, good.
Yeah.
Good. And you can see that I left in a dashed line for the rest of the circle that would have been cut out of. But the important part is that solid line there. So, and the center of it is right here, that gray mark. So if you were diagramming this with a mirror, if you had a compass like this, that would be a really good way to do that. You'd mark where the center is, you'd make an arc for the mirror, and then you would put the focal point halfway between the center and the radius, so it's half a radius. So what a focal point means is, and this is demonstrated in some of those videos, is if you've got a spherical mirror like this, and you're viewing through it something very far away, the light rays from that far away thing basically strike this and hit parallel to one another, and they are focused down to a point. This is why this kind of mirror could be used to start fires, say, by focusing the sun's rays onto a point. That point is called the focal point. And it's an important rule with any spherical mirror, and we'll see this again with lenses, that parallel rays, or rays coming in parallel to the principal axis, will be focused through that focal point. So I'm going to give you a moment to make sure you sketch this out. It doesn't have to be perfect right now to be able to illustrate this in your notes. But we should have an object over here, which I'll label. And that's the object that we are finding the image of. We've got our mirror over here. And this is a concave mirror, as the label up top suggests. And then F is our focal point. Okay, so there are 3 rays that we're going to trace in order to find out where the image is formed. And I'll list down how we're doing it as I'm showing you. So the first ray we're going to draw is from the top of the object, because we always align it with for ease, we always align the bottom of it with this optical axis. And it's going to go in parallel to the mirror. Like so. A parallel ray will be reflected through the focal point. So when I see this hits a mirror and it's going to be reflected, where is it going to go? I'm going to zoom in here. From that point, oops, wrong tool. That should be right tool. There we are. Through the focal point. And I will label that here. From the top of the object, parallel to the optical axis, and then reflected through the focal point. Okay, so that's ray 1 that we're going to draw. Ray 2, we're going to take and sort of do the opposite. We're going to go from the top again. All of these will be from the top, because then that'll define where the top is. And it'll go through the focal point. Okay, and a ray that goes through the focal point gets reflected parallel to the optical axis. Oops. So that's two of them, and two of them are actually enough to define where that's going to form, where that image will form. But there is a third option, and that's one that we draw to the optical axis on the mirror. That one gets reflected at the same angle of incidence. So this is just like a plane mirror in that case, where it comes in and it's hitting like the only perpendicular part to the optical axis. And so it gets reflected at the same part. The angle above the optical axis is the angle below the optical axis. So it's to the intersection with the mirror, and it's reflected at the same angle as incidence. So these three rays, when combined, will tell us the location of our object. And the way I set it up here, I've got very careful measurement, but not perfect. So that's why when we zoom in to see where those intersect, we see that it isn't quite a perfect point there. It's a little smudged right up here, but it is pretty close. You can get this close even with drawing on paper, provided you actually make this surface round, using a compass or something that is round as the mirror. Okay, so if the image is down there, what's it going to look like, or how is it going to be different from our original? I see everybody, a lot of people drawing. I'll give you a moment. So the image will be formed down by my cursor. But how is it going to be different from the original object?
Is it going to be upside down?
It'll be upside down. So I'm going to copy my object here and paste it, and we're going to put it upside down first off. Okay. And it's going to be that distance from the mirror. What else can you tell me about this object now, looking at the intersection and the mirror and just the copied object? So it's upside down is one of them, and I'm going to add that to my list.
Well, I've got a potential idea.
What do you think?
So if we're looking at intersections of all the lines,
Yep.
From what I see, they intersect at 2 points. One is with the new arrow, and the other one is where they all start. So wouldn't that second intersection also supposed to be the top of the object?
Bingo. Didn't know where you were going with that right at first, but yes. So that's the top of the object. And if we went down, I'm going to zoom in a little bit here quick. If we went down and did this same sort of ray tracing with other points along this, we would just see that they match up and get closer and closer to this optical axis. So if we took a point lower on it, we would just define where that image is lower on our image, so it would be approaching the optical axis from the bottom though. So what else is different other than it upside down? What can you now see about that image as well?
It's much smaller.
Much smaller. So demagnified. And then the last thing I want to say here is this an image that we could potentially put a card in that place and have the image projected onto the card? Is that image occurring in real space?
Yeah.
Yes.
Yep, we could put a card there. And that's one of the things that is demonstrated, and I think in the 4th video, where we could use this mirror and take an image coming in like this and then actually form it on a card. That means this is a real image, which is formed by actual rays in real space. This is different than what we saw with the plane mirror and a virtual image, where in real space, those rays never really intersected, so it didn't form an image that could be projected. But this one can be projected, and so it is a real image.
All right, I got a question about something that I don't think we can figure out just using these lines.
Okay.
Will it be flipped or will it not be flipped, like horizontally?
So for that, we're looking sort of from a side angle right now. But let's take this in our minds and rotate it so that instead of looking bottom to top, we're looking center to left, right? So I'm now looking like this at the image. We would do the same thing because this is a spherical mirror. It's symmetric in the X and Y directions. So if we were to look at it instead of from the side like this image is taken, if we were to look at it from the top and look at it like this, we would see that this would be, say, a left shoulder of a person who is looking at the mirror along this axis, and we're looking down on top of the head, and their left shoulder comes over here to the right side. So it is flipped not only up and down, it's also flipped left and right. This is something that you get from looking at the inside of a shiny spoon. If you lift your left arm, it looks like the right arm of the image. So you're flipped that way as well. So let's also put that upside down, flipped left to right. Demagnified, so it's smaller, and it is a real image, so it could be useful in projection halls or something like that. Okay. We're going to go on, but we'll wait for that till tomorrow because we have just a few minutes left. So are there any other questions you'd like to go over on this? Any other questions about how I did parts or anything like that? Okay. I'm just gonna pull up if I can. I can do this. Okay. Yep, tomorrow I plan to go through another couple of ray traces like this, different options with the mirrors that we've been looking at, the spherical mirrors. And then Thursday will be our reading 2 discussion. Now, we have been told that May 1st and May 4th are teacher work days for planning. And so we won't, and as it turns out, I didn't have those scheduled for official meetings anyway. My plan though is to still be online for office hours if at all possible. If I'm not taken up in a meeting during that time, I will still be here at 1 to 1:30 and available for chats, and I'll be checking email and stuff. So if you're working on the homework, 11.2, which by the way, even though we don't have meetings, you still have homework, then you can still contact me in the normal ways. If that is not the case, if I won't be able to be available during the office hour of 1 to 1:30, I'll send out an email to let you know. But I should still be available via email and potentially throughout the day if you needed to meet for something. I think that's all I've got. If you've got a question, and ask now.
Do we have any assignments for today that we need to complete?
Nope. And I think you had Lab B done. So that's what I wanted you to get done for this. We do have the reading 2 due by Thursday, but the talk today and the talk tomorrow will help support that. So it's not a terrible idea to wait until after tomorrow's meeting to chat about that or to read that.
Okay.
Okay, well, if there is nothing else, then I will bid you good day.